Hey there, gang. This is lecture 5.2, and again, I'm going to try to keep it short and sweet because I know how much you love sitting here watching these incredibly edited lectures. But the problem I'm giving you here says 3 neighborhoods are in need of a new cell phone tower. Now, these neighborhoods are some of the many neighborhoods in Pittsburgh, Pennsylvania, where I'm originally from. And the idea here is, where is the best place to put the tower? Well, of course, the answer is in the place that can reach each neighborhood, right? But where exactly is that? Well, we're going to be doing these kind of problems today that involve triangles and how to best utilize a resource. Okay? And this ties directly to perpendicular bisectors, which means the sides, and angle bisectors of triangles. And you can see here, there's all sorts of examples of this in modern architecture and urban planning that have to do, here's the golden triangle of Pittsburgh, that have to do with, are you equidistant to a side, or are you equidistant to a vertex, to a point? So tons of vocabulary here. Again, we talk about concurrent, where lines come together. A point of concurrency is where 2 or 3 or 4 lines come together. Circumcenter of a triangle, the point that is in the center. Well, what do you mean the center? Well, it's the point in which each corner is equidistant to that center point. Circumscribe means to make a circle around something. The in-center is a point equidistant to the sides, and inscribed means to draw inside. And again, you have these vocabulary terms, but they'll make more sense as we go ahead and apply them. So the first one we need to talk about is the circumcenter theory. Okay, get your jokes out now. Pause if you need to, laugh. Tell your buddy, Mr. Rising said circumcenter, right? It's a math term. Circumcenter, to go around. Circumcenter, the point in a triangle equidistant to the vertices. It means that these points, or these segments, PA, PB, PC, are all the same. And again, the way you find that is by taking the perpendicular bisector of each side. Well, that's cool. So if you have a triangle and you take the bisector, the perpendicular bisector of each side, you get a point that's equidistant to the 3 corners of the triangle. Very cool. What's so neat is, on an acute triangle, it's inside. In an obtuse triangle, that point is outside. And on a right triangle, that point is on the hypotenuse. Nice. So here's the problem. Z is the circumcenter of triangle GHJ, which tells you so much information right after that. Number 1, it tells you these, right, are perpendicular bisectors. That's really cool. The 4 things it tells you, I'm going to use the symbol 4, and I'm going to do it in red, is these segments are all also the same. So when it says, what's the measure of HZ? Well, it's the same as the measure of GZ. And that means it's the same as GZ, which means it's just 19.9. See, there's no math, but there's some geometry, and I guess geometry is math. Pause.
Michael Honeybine, please come find me.
And I hope Michael found Mr. Walker. The next question, LJ. LJ, this segment right here. Ooh, now how would I find LJ? That's a really good question. Well, wait a minute. I might have to do a little bit of math, because I have a right triangle. I do have a right triangle. So I've got a right triangle that looks like this. And I know this is 9.5. So, Dax, how would you find out what this third side here is? You're right. You'd use the Pythagorean theorem a little bit backwards. Let me get my picture out of the way. So you're saying, hey, I know the hypotenuse, 19.9 squared equals 9.5 squared, plus this side here, squared. So I subtract 9.5 squared from both sides. And warning, don't forget PEMDAS, you have to do the squarings first. So I pull out my handy calculator, and I say 19.9 squared minus 9.5 squared is 305.76. But now I need to take the square root of that. And I get 17.49. Whatever units that problem is in. Now, a little bit harder problem here. It says find the circumcenter of triangle HJK with vertices at 0, 0, 10, 0, and 0, 6. Well, you may recall that when you have a right triangle, the circumcenter occurs on the hypotenuse. Well, how do you find circumcenter again? Circumcenter is found by taking the perpendicular bisectors of the sides. Well, wait a minute. That's great, because if this is 10 units long, well, halfway is the perpendicular bisector. And the same thing is true with this vertical one here. 1, 2, 3, 4, 5, 6. It's 6. So halfway between 0 and 6 is 3. And guess what? I now know that that point right here is the circumcenter. In fact, I'll just show you something real quick. So this point, the circumcenter is 6, 3. Yay. If you don't believe me, let me pull out my trusty, hey, get out of there. Let me pull up the trusty tool here. I don't know if this is going to work on the page. I'll show my magic another time if I have to. I put the point there, stretch that out to touch. Right there. Looks pretty close. This works better in real life, but if I spin this around, boom! Look at that. I've created a circle that touches exactly all 3 of those points, and that's what's so cool about the circumcenter. The next thing we need to talk about is incenter. And again, the incenter of a triangle is equidistant from the sides of the triangle. Well, how do you do that? How do you do that is you bisect the angles, right? So if you cut this angle in half and draw a line through it, you cut this angle in half, draw a line through it, cut this angle in half and draw a line through it. They all come together. The point of concurrency, where they all come together, is right here, point P. Well, what does that create? What that creates is a circle inside that triangle that touches all 3 sides like that. That's where the urban planning thing is. This point P is equidistant to the sides. Now, unlike the circumcenter, the incenter of a triangle always occurs inside the triangle. All right, fair enough. So let's take a look. What does that mean? You're done. Let's hit this hard on Tuesday.